We are starting with the preparation of phenol, which is also known as carbolic acid in this lecture. Carbolic acid, why? Because it was first time extracted or obtained from coal tar. So phenol is also known as carbolic acid. The first method that I'm starting with is the Dow's process. Dow's process you have already studied in the previous chapter, haloalkanes and haloarenes, right? And this is how the process takes place. We start with chlorobenzene and make it react with aqueous sodium hydroxide at 623 Kelvin temperature and 300 atmospheric pressure. Then what happens? H plus separates and ONA takes up the negative charge. Now the Cl minus ion, the leaving group, along with H plus forms HCl, and benzene gets substituted with ONA. Okay, benzene gets substituted with the ONA part, which is the nucleophile, right? In place of Cl, what comes is ONA. And the species which is formed, this one is known as the sodium phenoxide ion. Okay, this is called the sodium phenoxide. Now this is not the last thing. The sodium phenoxide which is formed is then further acidified. So using any dilute mineral acid, it can be acidified, and on acidification the sodium is replaced by hydrogen H plus, and that gives you phenol. So this is how by Dow's process using chlorobenzene phenol can be prepared. The second method which is used to prepare phenol is from benzene sulfonic acid. So this is from benzene sulfonic acid. Let's see how we can prepare benzene sulfonic acid first, and then from that phenol. So here we start with benzene, and benzene is straight away made to react with concentrated sulfuric acid. Okay, this process is called sulfonation, and which group is introduced on the ring is SO3H. So what is taking place here is sulfonation, which that will introduce SO3H group, and this is the benzene sulfonic acid. Now this compound, like the previous method, that is the Dow's process, is number 1 treated with aqueous sodium hydroxide, and number 2 followed by hydrolysis. So same steps as the Dow's process. First reaction with sodium hydroxide, and second acidification. And what happens? This group is first replaced by ONA, and later Na is replaced by hydrogen, and that gives you straight away phenol. Okay, so this is how benzene sulfonic acid on reaction with NaOH followed by hydrolysis gives us phenol. So this was the second method. The third method is from benzene diazonium salt. Even benzene diazonium salts we have talked about in the last chapter, that is haloalkanes and haloarenes, right? Let me then remind you how these were prepared. Here we start with aniline, which is an aromatic amine, and we make it react with NaNO2 and HCl, sodium nitrite and HCl, at 0 to 5 degrees Celsius, and this forms the benzene diazonium salt, which is benzene with N2 plus Cl minus. So this is your benzene diazonium chloride. It's a diazonium salt, benzene diazonium chloride. Now this benzene diazonium salt, when is simply warmed with water, okay, on simply warming it with water, the entire group here gets replaced by OH, and what you get is phenol plus nitrogen HCl as byproduct. So the benzene diazonium chloride formed on warming with water forms phenol, right? This was the third method. And the fourth and the last method that we take up here is from cumene, using cumene. Now cumene is a common name of a compound which is called isopropyl benzene. So cumene is the common name of a compound which is isopropyl benzene. So let's start with cumene. What is cumene? As I told you, cumene is isopropyl benzene. So we are attaching the isopropyl group on the benzene ring. CH3CH is the isopropyl group. So this is cumene or your isopropyl benzene. The first step is its oxidation. Okay, so what happens is cumene undergoes oxidation with oxygen. And what it forms is written as, how you can remember to write this intermediate formed is, keeping everything else the same, just that in the CH bond you have to insert the two oxygen atoms. So it forms COOH. This compound which is formed is known as the cumene hydroperoxide. The oxygen to oxygen linkage is known as the peroxide linkage. So this compound formed is cumene hydroperoxide. And now this cumene hydroperoxide, when is hydrolyzed, that is made to react with water, it gives us phenol plus another very important byproduct, which is acetone or propanol. Now how this is formed is, how you can remember is, this was your cumene hydroperoxide. So from here, keep the last OH group. That last OH is going to be retained on the benzene ring. So benzene, when will retain this OH, what will it form is phenol. This bond will break. And now imagine from the remaining portion, what do you get? CH3C. This bond becomes a double bond. So CH3C double bond O CH3, that's your acetone. So benzene will retain the OH forming phenol, and this remaining portion forms the byproduct, which is acetone, which is also obtained in a good substantial amount. Okay, so this was the last method from cumene, which is isopropyl benzene. By oxidation followed by hydrolysis, phenol can be obtained. Now we are going to take up the physical properties of alcohols, phenols and ethers, all the three together. The first physical property that we talk about is boiling point. Okay, and whether it's an alcohol or it's a phenol or it's an ether, this point is a common point. And what is the point? That with increase in the number of carbon atoms, with increase in the number of carbon atoms, boiling point increases. With increase in the number of carbon atoms, boiling point increases because surface area increases and the van der Waals forces also increase. So what's the reason why with increase in the number of carbon atoms the boiling point increases? Is because when the number of carbon atoms increase, the surface area of the molecule will increase and the van der Waals forces are also going to increase, and therefore boiling point also increases, right? Number 2, I am still in boiling point, so I can make it to 1A and this can be made to 1B. So we are still discussing boiling point. Second point in boiling point B is with increase in branching. With increase in branching, boiling point decreases. The more branched it's going to be, it will have a lower boiling point. So with increase in branching, boiling point decreases due to decrease in surface area and van der Waals forces. This point we have already discussed in the previous chapter also, that when the branching increases in a molecule, its surface area decreases, and when the surface area decreases, the van der Waals forces are also going to decrease, and hence the boiling point also decreases. Okay, so with increase in branching, boiling point will decrease. And remember, this point particularly is for isomers. This is particularly for isomers having the same molecular formula. Compounds having the same molecular formula, which are the isomers. For such compounds, when there will be more branching, the surface area will be less and the boiling points are going to be less. Okay, now let's talk about the third point in boiling point itself, and this is alcohols and phenols have boiling points higher than ethers and hydrocarbons of comparable molar masses. So alcohols and phenols, they have boiling points which are higher than ethers and hydrocarbons of the comparable molar masses. And this is, you can say, I'm writing the reason, then I'll explain. Because they undergo strong intermolecular hydrogen bonding. Because they undergo intermolecular hydrogen bonding, that's why their boiling points are higher than the ethers and the hydrocarbons. Let me show how the alcohols and phenols, they form hydrogen bonds. Let's say ROH represents an alcohol. Okay, ROH is any general alcohol, and the charge separation that is going to take place in the alcohol is oxygen more electronegative, partial negative, and hydrogen partial positive. And now if there is another molecule of the alcohol in the vicinity, okay, let's take it as ROH. This is another molecule of the same alcohol in the vicinity. Here also the oxygen will be partially negative, more electronegative, hydrogen will be partially positive. And now what happens between these two molecules? The partial negative oxygen of one molecule and the partial positive hydrogen of the second molecule, they will enter into hydrogen bonding between two molecules. Therefore this is called intermolecular hydrogen bonding. So this is how molecules of alcohol are going to join with each other. The same thing happens in case of phenol also, and let me explain that also. This is phenol, C6H5OH. Same thing here also, oxygen partial negative, hydrogen partial positive. That's always because of difference in the electronegativity. And now let me take up another molecule of the same phenol, C6H5OH, hydrogen partial positive, oxygen partial negative. Now when two such phenol molecules will be nearby in the vicinity of each other, the positive hydrogen of one will form intermolecular hydrogen bond with the negative oxygen of the other molecule. So this is how you can see that alcohols and phenols, they enter into hydrogen bonding, which is quite strong, and therefore their boiling points are higher. To sum it up, I'll write in the form of an example. Let's say I take CH3, CH2, CH3. This is propane. It's a hydrocarbon. Then another example I take is of methoxy, methane, which is an ether. And finally, I'm taking example of one alcohol, CH3, CH2OH, that is ethanol. Okay. Let's write the type of bonds which will exist between the molecules. As you just saw, in alcohols, the bond is going to be hydrogen bond. There will be intermolecular hydrogen bonding. Now, what type of forces are going to be there between ethers? Ethers are going to have dipole-dipole interactions. Dipole-dipole interactions or dipole-dipole forces. Why? Because ethers are polar in nature. Ethers have some polarity, some charge separation. Again, because of the electronegative nature of oxygen with respect to carbon, there will be some charge separation, some polarity. So I'm mentioning here ethers are also polar. They have polarity. And when they are polar, the type of forces which will be there between the molecules are going to be dipole-dipole interactions. Now, you know alkanes? Alkanes are completely non-polar. And therefore, the only type of forces which are possible here are the van der Waals forces. The van der Waals forces, which you know are the weakest. So can we say that as I am going from the hydrocarbon to the ether to the alcohol, the strength of intermolecular force of attraction increases. the strength of the intermolecular force of attraction increases. And when the strength of the intermolecular force of attraction will increase, the boiling point also increases. So I can say more than the hydrocarbon, ethers will have higher boiling points, and more than the ethers, alcohols will have the higher, will have the highest boiling point among the three, right? So what is the reasoning here? As the strength of the intermolecular force of attraction will increase, the boiling point is also going to increase. So alcohols maximum because of hydrogen bond, then ethers less than that because of dipole-dipole interactions, and least is going to be the alkanes because of the weakest van der Waals forces of attraction. Now the second property that we talk about is solubility. Okay, so first of all, let me just tell you the fact that alcohols, phenols, and ethers, okay, alcohols, phenols, and ethers, all the three are soluble in water. All three are soluble in water because these can form hydrogen bonds with water. If an organic compound is able to form hydrogen bonds with water, it will be soluble in water. And alcohols, phenols, and ethers, all three are capable of forming hydrogen bonds with water. So they are soluble in water, all of them. Let me show how they form hydrogen bonds with water. Let's take example of an alcohol first of all. ROH. ROH, what is this? This is an alcohol. Oxygen with two lone pairs is what charge? Negative. And hydrogen takes up a partial positive charge because oxygen is more electronegative than hydrogen. O minus, H plus. Now this O minus can form a hydrogen bond. Even the H plus can form a hydrogen bond. In fact, let me tell you one more thing. O minus can form two hydrogen bonds at the same time. Why? Because of two lone pairs. The oxygen atom with two lone pairs can form two hydrogen bonds at the same time, and H plus can form one. So that means a molecule of alcohol can form three hydrogen bonds at the same time. Now it has to form hydrogen bonds with water. Okay. Now water is H2O. Certainly the H plus has to form a bond with O minus. So carefully, okay, write the same. H plus will form a hydrogen bond with O minus from water. In water, the charge separation will be again H plus and O minus. So this is 1. Now oxygen will form hydrogen bond obviously with what? H plus from water. So let's say this is H2O. This is another molecule of water I have shown here. H was positive and O was negative. So H plus forms a bond. And here also with this oxygen, what will form? H plus will form. So you can show another molecule of water here, H plus forming bond with O minus. So this is how one molecule of an alcohol can form three hydrogen bonds with water, and hence they are soluble in water. Exactly the same manner, no difference at all, phenol can also do the same thing. So if I consider molecule of a phenol, which is this. So this is your phenol, and you already know the charge separation. It will be H plus and O minus. So H plus can form a hydrogen bond with water's oxygen. Positive always connects with negative. So H plus forms with the oxygen atom from water. And O minus, right? As you know, O minus can also form. It will form with H plus from water. So negative part forming bond with H plus. Okay. And certainly you can show oxygen forming one more. I just told you that oxygen at the same time can form two bonds. The reason is because it contains two lone pairs. So simultaneously it can form two. So again a molecule of phenol can form three hydrogen bonds with three water molecules and dissolves in water. Now let's take example of one ether also. So let's say I take example of a general ether which is ROR. Now here, it is only the oxygen atom which can form hydrogen bonds. The alkyl part cannot. Bond can be formed by only oxygen atom here, or otherwise it can be formed by H plus. But as you see, there is no H plus attached to the oxygen. So hydrogen bond is going to be formed by only the oxygen atom. But then how many? 2. Okay, because oxygen contains 2 lone pairs, it can form 2 hydrogen bonds at the same time. Obviously with what? Hydrogen from water. Likewise, this will also form hydrogen bond with the H plus facing the O minus. So this is how one molecule of ether can form 2 hydrogen bonds, 2 intermolecular hydrogen bonds with the water molecule. So you have seen that all the 3, that is alcohols, phenols and the ethers, all 3 are capable of forming hydrogen bonds with water, and so they are all soluble in water. Okay, now I'll just conclude it with one more thing. And what is that? As the size of R, what is R? The alkyl group. As the size of alkyl group increases, solubility in water decreases. As the size of the alkyl part increases, solubility in water decreases. The reason is due to increased hydrophobic interactions. This is due to increased hydrophobic interactions. What is hydrophobic? Hydrophobic is water repelling. Due to increased hydrophobic interactions, which is water repelling properties, right? So how am I explaining this is, suppose you take alcohol as CH3OH, then you take the second alcohol as CH3CH2OH. Let me just compare these two. Now this is the alkyl part, okay, and it is observed that methanol is more soluble than ethanol. Why? Because this alkyl part, this alkyl chain is hydrophobic. It is water repelling because there is no charge separation. Okay, so this part is hydrophobic or water repelling. Now when this part is going to increase, there will be more hydrophobic interactions, and that is why the higher alcohols are going to be less soluble. You may even write one more example here. Let's take propanol. So it will be the same order. As the size of the alkyl part is further increasing, it will become less soluble. So from methanol to ethanol to propanol, you can say the solubility in water decreases. With increase in the size of the alkyl group, which is hydrophobic, solubility in water is going to decrease. And for the same reason, I'll just give one last point, that alcohols are more soluble than phenols. Alcohols are more soluble than phenols. Why? Why are alcohols more soluble than phenols? Because in phenol, you can see here that there's a bulky benzene ring. And this bulky benzene ring is going to be more hydrophobic. Here also there is no charge separation, so this is also more hydrophobic or water repelling. And therefore alcohols are more soluble than phenols in water.